Hello everyone, this is our submission for GDSC project, Local LLM Instrumentation, Tracing and Replay Platform. Our project extends llama CPP by instrumenting its execution pipeline in real time and visualizing tensor level activity through an interactive terminal dashboard built using FTX UI. So modern LLM inference engines execute hundreds of tensor operations internally, but these computations are usually invisible to the developers, and debugging numerical instability or understanding attention behavior or even analyzing performance often requires heavyweight profilers. So our goal was to build a lightweight instrumentation layer that captures tensor execution in real time and presents it through an interactive terminal interface. So our instrumentation is built around llama cpp cb eval callback. Every time ggml evaluates a tensor, our callback receives that tensor, and we extract metadata such as tensor name, operation type, shape, latency, sparsity, numerical stats, timestamps, anomaly detection, etc. These are packaged into a trace event object and is pushed into a thread safe ring buffer. And the UI runs on a separate thread and continuously reads this buffer to update the dashboard in real time. So let us have a live demo. So on the left, we have is the hierarchical model topology. Each transformation layer can be expanded to reveal its attention and MLP submodules, and I can use keyboard for navigation. So on selecting the attention module, it changes the runtime metrics inspector accordingly to display attention computations for that layer. Similarly, selecting the MLP module displays feed-forward tensors such as FFN Swiglu, allowing us to inspect that stage independently. On the right, we have a package stream which displays most recently executed tensor operations. For every tensor, we show tensor name, GGML operations, latency, and compute device. In the bottom, we have attention matrix visualizer, which basically whenever a KQ softmax tensor is observed, we capture its attention weight and render an SKY heat map representing the first attention head. Just above, we have a numerically anomaly ledger, uh, which basically monitors tensors for numerical anomalies. And it currently detects NaN values, infinite values, large activations, clippings, etc. Any detected issue is immediately recorded in the anomaly ledger. So in the bottom we have our status bar. Using tab we can cycle the focus. J and K can be used for keyboard navigations. Using space we can select the layer, attention and MLP modules, and using Q we can quit the screen. So let us have a code walkthrough. So like this is our trace event underscore event.h file. So before discussing the instrumentation logic, let's first discuss the core data structure that powers the system. Every tensor operation is represented by a trace event, and this structure stores all the runtime information that we want to visualize in the dashboard. The name is something that identifies the tensor being executed. OP here is basically storing GGML operation types such as matrix multiplication or softmax. Then we have a timestamp which captures wall clock time at which the tensor was evaluated. And then we have the shape which are tensor dimensions. Then we have latency underscore US, which records the execution latency in microseconds. Then we have mean max underscore ABS sparsity, which provide numerical stats that help us to analyze tensor behavior. Then we have has NaN, has INF, is clipping. These are used for anomaly detection. Then we have attention data here, which is basically storing raw attention weights so that they can later be rendered as an ASCII heat map. So each tensor evaluation produces one trace event, which becomes the basic unit flowing through our visualization pipeline. Now let us visit our src and main.cpp file. Uh, so in our src folder, we have this main.cpp file, and as you can see, there's this function bool my underscore callback, which is a heart of our instrumentation layer. And here, this trace event EV is basically every time ggml finishes evaluating a tensor, llama cpp invokes this callback, and we immediately create a new trace event for that tensor. Then you can see EV dot name, ev dot op, ev dot shape, ev dot latency underscore us, and ev dot timestamp. So basically we are extracting metadata such as tensor names, operation type, tensor dimensions, execution latency, and timestamp. So for floating point tensors, we compute stats like mean, maximum, absolute value, sparsity. Then we have this part which also performs anomaly detection by checking the NaN values, infinities, clippings, and unusually large activations. Then this basically we are finally the completed event is pushed into a thread safe ring buffer, and the model thread continuously produces trace event. And then we have a renderer. The user interface is implemented using ftxui, and in the renderer basically the it periodically reads the latest events from the ring buffer and updates all the dashboard panels. Then we also have different panel variables such as metrics panel, anomaly panel, attention panel. Like each panel is constructed independently. For example, runtime metrics inspector displays stats for selected layer or submodule. Here, these are the panel variables. The numerical anomaly ledger lists detected anomalies, and the attention matrix visualizer renders attention weights whenever they are visible. So overall, the architecture cleanly separates instrumentation from visualization, and the callback captures runtime information. The ring buffer transfers it safely between the threads, and the renderer presents it interactively without interfering with the model execution. So this was our project. Thank you.